Welcome everybody at day 9 of Climate Match Academy on climate response, extremes and variability. My name is Yuri Reinders. I will take you through 9 tutorials today that are discussing how to study extreme events within the context of climate change, specifically thus how these extreme events are going to change and how we know that. I work at Leiden University College. There I do research mostly on flooding and how that changes with climate change, but also other extreme events like droughts or wildfires. For this first tutorial, we're going to talk about distributions. The objectives are basically for you to see a time series of a climate variable, for example, a time series of temperature or stream flow, and to turn it into a distribution through a histogram and by calculating the moments of that distribution or of the record. So, for example, the mean and the variance or the skew, and then how to construct the distribution through that. But before we do that, first I think we need to put this topic a little bit into context. Why is it important to study extreme events in a climate change course? Most of you, when we talk about climate change, we'll talk about things that happen in the future, for example, projections, scenarios, and those type of things. But extreme events are how we already experience most of what's going to happen due to climate change. We see that storms are rising, or intensity of storms are increasing, the frequency is increasing, droughts are increasing. Here you see an example of a drought in Eastern Africa. And what becomes most apparent also from figures like this, perhaps also pictures you have seen somewhere else, is the impact that it has on livelihoods. It's a social, it breaks down sort of the social ties, and therefore it's important to adapt to it. This happens, by the way, around the world. It's not only something in the global south, but for example, here in the United States, we also have big issues with flooding. And quantifying the impact of change that climate change has on extreme events, for example, through frequency or intensity or timing, can help us to really develop proper adaptation strategies or evacuation strategies or infrastructure that should reduce the impact on vulnerable communities of these extremes. So that's why it's important. Often you'll find or encounter a record like this, something like a time series, where you have a bunch of dots on a timeline. Here we see, for example, annual peak stream flow. So this is an extreme variable. It's the most or the highest stream flow record recorded in a certain given year. So for each year up to about starting to be systematic around 1927. Now, as I said, these are already extremes, but you can see that not all the extremes are similar, right? There's a bunch that clutter around this extreme average, and then there are a bunch that are more extreme, and those are the ones that are problematic. Those are the ones that cause flooding, or in the case of precipitation, a storm event, or in the case of a temperature, a drought, etc. Here you see that there are only about 6 of those extreme events cases, and that over about a 100-year period or a 100-year timeline. So that's very little data to go out. So how can we then assess changes of extremes over time if we have only so little data to account for? One strategy is by making a distribution, something that looks like this. Here we're transitioning, by the way, to temperature data in the build in the Netherlands. And I want to encourage you to think about these climate variables, whether it's temperature, rain, or wind, as distributions rather than, for example, climate normals or the mean average, something like that. So here you could say the average or the climate, in the case of temperature, is 10 degrees Celsius in the build. However, it's much more interesting to consider the whole range of possible values and the chance that they happen. For example, it's much less likely that we'll find 0 degrees or 30 degrees. If we think about climate change, then we can assess that as a change in the distribution. For example, here you see a clear shift towards higher values in the second half of the 20th century compared to the first half, blue versus red. A shift in that distribution tells you something about how all the values, all the possible values are going to change. tails, so the ends of these distribution, are what contain the extreme events. So the ones that we are particularly interested in. Here you have, for example, the low extremes and the high extremes. We're now going to look mostly at the high extremes. Now, if we think of climate change, we want to see how those tails also change. So we're not only interested in the shift of the distribution, complete shift, but also in how the tails get thicker in this case. So you can see that in the case of the red distribution, the tails are a little bit thicker, meaning that the extremes are becoming more likely, less than just, or more contextual than only more extreme things are getting extremer. So you see how variance and things like intensity are playing a part in this too. So how do we go from a record that we have seen before to a distribution that we can then study for the tails? One way of doing this is by starting to make a histogram, which shows you the frequency of a given variable range over your recorded time. So here you can see there is a higher chance that that these values will be in the middle. They appear more, their frequency is higher than the ones at the end of the tail. So this already has the shape of that distribution line that I showed you before. The next step will be to compute the moments of our data. So those are, for example, the mean, the variance, and the skew. They describe how this distribution, this line looks like. The mean tells you its position, the variance how thick it is, and the skew how different the two sides of the distribution are relative to each other, or how thick the tails are, we sometimes say. So the mean here, for example, if we look at the build data, was indeed around 10 degrees Celsius, whereas the variance tells you something how far, like how fast the values around it spread. So if the variance is very low, most of the values are around the mean. The opposite is also true. Now, from those moments, we can estimate parameters from distributions. The most iconic is the normal distribution. You probably have heard about that one in some statistics class, and that's the first one we're going to try out here too. So the normal distribution is created from the mean and the variance, or the mean and the standard deviation. There's a whole mathematical formula to describe this, which we're not going to get into, but we can, from that mathematical formula, infer based on that mean and variance how big the chance is that you're going to find some temperature probability. And that line, the line that we have seen before, is what we call the probability density function. So again, the peak of the probability density function is the value, in the case of the normal distribution, the mean, the value that we have the highest chance of seeing on any given day, so about 10 degrees. Probability density function is what we will use quite a bit throughout this set of tutorials. And I want to make you aware that, again, we made an assumption here. We assumed that we would use the normal distribution, or that the normal distribution would fit well. Now the question is that the case? Because there are also other distributions, so maybe another distribution would be better. That is for you to explore in this tutorial. I will see you in the next one.